The last section we're going to look at is the pH of strong acids and strong bases. And that's because these are really easy to adapt to what we already know. This might be covered later in the book. I was having a little trouble finding it, but it's something we can tack on now and finish really quickly. Now, I probably should stop there at 16.6, but I like to talk about the strong acids and strong bases because we can walk through this in 1 minute, right? And it's not hard. And that's because strong acids dissociate 100%. So if you have exactly 1 mole of HCl, you get exactly 1 mole of H+. So therefore, if you have 1 molar HCl, you have 1 molar H0+. pH is very easy to find. Again, pH of a 1 molar HCl solution is just the negative log of 1, which works out to 0. Again, that doesn't mean you have no acid. It's just a dumb logarithmic scale. But you can do this with any concentration. 0.03 molar HNO3, just take the negative log and we get a pH of 1.52. Again, it's worth pointing out that a pH of 0 is about when this acidity starts to get dangerous, right? In large quantities, a pH of 0 can be really dangerous. Most of the time, I'm more worried about a pH of negative 0.5 to negative 1, though. We can also do the exact same thing with bases. Now, it's a little bit more work because we have to go through the POH, but it's not that much more work. If you have a 0.1 molar solution of NaOH, we are going to assume it dissociates completely, so that's going to create 0.1 molar OH-. The POH is just going to be the negative log, so we will have a POH of 1, and therefore our pH is 13. Makes sense, right? We put a basic solution, we get a pH above 7. And that is a good kind of thought to keep in mind as you do these problems. A lot of times, these are so easy that people rush, and they say, oh, yeah, pH of 1, and they just throw it in. When actually, right, you can't get an acidic pH from a base. So it's important to kind of recognize these bases and say, oh, okay, this pH has to be something larger than 7. Now, when it comes to something like BaOH2, because these 3 bases in group 2 have twice as much OH- per molecule, we have to consider that in our calculation. So 0.1 molar BaOH2 actually creates 0.2 molar OH-. If you take the negative log of 0.2, we actually get a pOH of 0.7, which means the pH is 13.3. So again, the logarithmic scale is weird. Every time you go up a pH of 1, your OH- gets 10 times stronger. So, doubling it only brings your pH up by 3. All right, so really quickly determine the pH for each of these solutions based on the concentration. Okay, well, HCl is really easy. If we have 3.45 times 10 to the negative 4th molar HCl, that means we have 3.5 times 10 to the negative 4th molar H0+, which means we just have a pH of 3.46. Now, NaOH means we have the exact same concentration of OH-. You can either do this by going through the H0+, through the Kw, and then solving for pH. Again, my preference is just to solve for the POH and then solve for the pH after. Either way, we get a pH of 9.38. Again, it makes sense. We add a base, we get a basic pH. All right, try these as well. Again, it's very simple for the acid because we're asking for the log of H0+, which will be the same as the concentration of HNO3, so we get a pH of 5.33. For something like CaOH2, we have to double that OH- concentration, which is going to give us either 16.6 times the negative 3 or 0.0166 molar OH-. So if I take the negative log of that, I get a pOH of 1.78 or a pH of 12.22. Now, this last thing is probably not something I'll have an exam question on. Probably don't have a homework question on this either because it's not much in the book. But it's worth bringing up that pH is so kind of ubiquitous. People say it all the time. It's really easy to get confused by the fact that pH doesn't really mean anything. So this should be a simple dilution for any concentration. If 500 milliliters of a pH 4 solution is added to 500 milliliters of water, what's the new pH? And people say, oh, well, we're diluting it in half, so the pH should divide in half. So the answer should be A, pH of 2. If you think about it, that doesn't make any sense. A pH of 2 is more acidic, so it can't be A. People say, oh, well, then it's the other way around. It's pH of 8. No, because you can't add water and make something basic. So it's obviously not 4, so we're down to these other two numbers. So we've got to think about, and you can probably think about it a little bit if you rationalize that each pH is a power of 10, what answer makes sense. But let's walk through how you'd solve something like that. All right, so it's worth keeping in mind, anytime we're doing a calculation with pH, we want to switch to H3O plus and a real concentration. So our H3O plus concentration here is 1 times the negative 4th molar, and it's a 500 milliliter solution. Now, what I'm going to do is use the molarity equation to find the moles, and then put the moles over the new volume. Now, the easier way to do this is probably just to use the dilution equation as we did before, but this comes up again in chapter 17 in a similar format, so I'm just kind of writing it to look like that. So what I've done is taken the molarity times the liters, and that gives me the moles. This is kind of a funny way to write this number, but it works. I end up with 0.5 times the negative 4th moles divided by the new volume of 1 liter. That gives me 0.5 times the negative 4th molar. If I plug that into the pH, I have a new pH of 4.3. Again, the pH is going to become less acidic, but not by a full power of 10, so it just changed inside of a pH of 4. So you can try this one really quickly. 20 milliliters of HCl waste has a pH of 4.5. If you dilute to a total volume of 400 milliliters, what's the new pH? If we have a pH of 4.5, that gives us an H3O plus concentration of 3.16 times the negative 5th molar. If we multiply that times the volume, we end up with 6.32 times the negative 7th moles of H3O plus. Now if I put those moles over the new liter, that gives us a new molarity of 1.5 times the negative 6th, or a new pH of 5.8. Again, that's essentially an increase in volume by about 20 times, or about 1 1/3 pH, which is about what we have here. Okay, so again, I'm saving all the stuff with weak acid, weak base equilibrium until after the next exam. I really want to make sure you are comfortable with pH calculations, you are comfortable with equilibrium and ice tables, and then after the exam, we're going to push all this stuff together and finish off chapter 16.